Hello everyone. In this video, we are going to talk about stability analysis of discrete time systems. And before I start, I need to mention that pictures and equations are taken from Discrete Time Control Systems by Katsuhiko Ogata, which is one of the best textbooks out there for digital control. So one of the important thing is, of course, when you have an analog system, you want to convert it to a digital system. And one of the theoretical methods that used for analysis of discrete time system is we use what we call impulse sampling. What is that? So basically it's like a switch that you turn on and off, and when it goes on for a very small duration of time, then you get one sample out of the analog signal, and then you open it, and then again at regular intervals where the sampling time is this capital T here, you go and get samples out of the analog signal. So this analog signal on the left will be converted to this digital signal on the right, and as I said, the time between these samples is called sample time, or T. So you can say that the sampled signal, which you can show by x star t, is what? Is the summation k goes from 0 to infinity of x of kt times delta of t minus kt. And this delta is the impulse function, okay? And or a canonical delta function in this case, actually, which has a magnitude of 1 at time t equal kt, and elsewhere it is what? It is basically 0. So if you look at this, it is 1 when t is equal to k times t, and basically 0 else. Okay, and so by adding all of these impulses, you can get what? The x star t, the impulse sampled signal. Now, if we want to look at the Laplace transform of this x of t, which we call cap x of s, basically you know that what we need to do, we need to apply the Laplace to the delta function, right? Because clearly these x's of kt, these are just some numbers. So if you expand it, it is going to be what? It is going to be x of 0 times Laplace of delta of t. So here k0, then it's going to be x of t times Laplace of delta t minus t, and so on and so forth. And of course, Laplace of delta, as you know, is 1. Laplace of delta t minus t, it's 1, and then this is a delayed version of the signal, so it's going to be multiplied by e to the negative ts. This next one is going to be basically 1 times e to the negative 2 ts, and so on. So if you write it, it is going to be like that: x naught plus x of t times e to the negative ts, x of 2t, e to the negative 2ts, and so on. And if you want to write it as a summation, it's going to be summation of x of kt, e to the negative kts, as k goes from 0 to infinity. So this is what? This is the Laplace of this sample signal, okay, the digital signal. Now that you have that, I want you to pay attention to how close this one is to the Z transform. If you remember, the Z transform of a signal, if you remember, it was what? It was a summation as k goes from 0 to infinity of x of kt z to the negative k. This was what? This was the Z transform of a discrete time signal. And if you look at these two, they are very similar. All you need to do is to replace what? E to the ts by z. If you just do a change of variable here and replace e to the ts by z, guess what? Then you can say that the Z transform of the discrete signal is what? Is the Laplace transform of the sample signal, right? And again, the way that you go from the Laplace domain to the z domain is by this change of variable e to the ts equals z, or if you want s versus z, z is 1 over t natural log of z. Okay, so if we use either this or this, we can go from s domain to the z domain, or here on the right we can go from z domain to what? To the s domain. Okay, so this is the change of variable that we need, and that is sufficient to tell us how we do a stability analysis in the z domain. How? Because guess what? If you remember, when we used Laplace transform, what was the criterion for stability? We said that the closed loop poles of the system should be what? If this is the imaginary plane, right, or the complex plane, and this is the imaginary axis and this is the real axis, we said that all of the poles should be on the left-hand side of the imaginary axis. Then the system is what? Stable, huh? Yeah. So now we want to know, as we go from this S-plane here to this Z-plane, and their transformation, as you just saw, is Z equals what? E to the TS. What is gonna happen here? Okay, so what we need to do is consider the S to be an arbitrary complex number like sigma plus j omega, and plug it into this formula, z equal e to the ts, so z becomes e to the t times sigma plus j omega. If you separate it, it becomes e to the t sigma times e to the tj omega. And you know, this portion has a magnitude of 1, so the magnitude of this z is actually this e to the t sigma. Okay, and clearly, since this complex part, this complex exponential e to the jt omega is a periodic function, so whether it's j to the t omega or e to the j times t omega plus 2 pi k, the answer is going to be the same. Okay, because you know, based on the Euler formula, e to the j t omega is cosine t omega plus sine t omega, and cosine and sine functions are periodic with 2 pi or any multiple of 2 pi. So clearly, it doesn't matter that whether you plugged in omega here and sigma for s, or you plugged in what? Sigma plus j times omega and then plus 2pk. Okay, so basically you can see that for several different values of omega and the same sigma in the S domain, you're going to get a single what? Z value, and that's exactly what you see here on the left. You can see that if my point is, let's say, here, or it's right above it here with 2 pi increase in frequency, or 4 pi, or negative 2 pi, or negative 4 pi, all of these will end up to be what? The same point in the z-plane. Okay, so going from s to z is not a 1-to-1. There are so many, infinitely many s values for which the z is a single value. Okay, but what we care about here right now more is what happens to this left side of the imaginary plane, that is the region for stability. What happens to that? Well, clearly, you know that in this left side, sigma, which is the real part, okay, right? Sigma is the real part. The sigma has to be negative. If that's the case, then the magnitude of z, which is this e to the t sigma, is going to be e to the negative part, and exponential of any negative number is going to be less than 1. So what does that mean? Means, and magnitude of z less than 1 is clearly what? Anything inside the unit circle. You see that? So the left half plane is corresponding to what? Corresponding to inside the unit circle. And the imaginary axis itself, the imaginary axis clearly here, where sigma is 0, correspond to what? E to the 0, which is what? Which is 1. So the imaginary axis corresponds to the unit circle, and anything to the left of the imaginary axis corresponds to what? Inside the unit circle. On the other hand, anything on the right side of the imaginary axis, which is this area, corresponds to e to the positive number, which is bigger than 1. So it is going to be what? Outside the unit circle. So outside the unit circle means unstable. Inside the unit circle means stable. On the unit circle means what? Marginally stable. So let's go ahead and write it down here. Okay, so here I added them for you. So you remember that as long as the poles of the closed loop system are inside, outside, or on the unit circle in the z-plane, that means stability, critical or marginal stability, and instability. Okay, and this is what we can clearly see from this simple what? Transformation formula. Okay. So, and as I said, there is no unique S. There is no one-to-one relation between S and Z. There are infinitely many S's that corresponds to a single Z. So the region in the S-plane that is only for omegas between omega S over 2 and negative omega S over 2, we call it the primary strip. Okay, that corresponds to basically all of the data inside the unit circle. And then the complementary strips are where the omega is bigger than omega over 2 or less than negative omega over 2. They also correspond to the areas inside the unit circle. And you might say, why would you call that center one the primary strip? Because here, as I just mentioned, here the frequency omega is between what? Is between negative omega s over 2, right? And omega s over 2. And omega s is what? That's the sampling frequency. And you know that if you don't want any problem with the sampling, you don't want any aliasing, any problem, your sample, your frequency should be what? Your maximum frequency omega should be less than or equal what? Omega s over 2, or you can say that your sampling frequency should be at least twice as high as the maximum frequency in the system. That is called the Shannon-Nyquist sampling theorem. And if that's the case, then you can always reconstruct what? You can reconstruct the analog signal from the digital signal back, okay? So if you want to go back later with a D to A, you can do it as long as you are inside that primary strip, okay? And there will be no problem in the system. So we assume that our sampling is done at such frequency, omega s bigger than or equal to omega or less than or equal negative to omega in magnitude. And for that reason, we assume that we are staying inside the primary strip, okay? Our sampling frequency is high enough, and for that reason, we just focus on the primary strip. But remember that this conversion is not one-to-one. Now, one of the methods that we have that you can find whether a digital system with a transfer function has any roots inside the unit circle, any poles inside the unit circle on it or outside it, is this method called Jury's stability test. This is kind of like the Routh-Horwitz. Remember the Routh-Horwitz test that we had for the S-domain, right? For continuous systems. And we formed a table. This is very similar. This here you also form a table. And this is also for a transfer function. So here we assume that your transfer function C over R is G over 1 plus GH. So basically your characteristic polynomial is the denominator 1 plus GH equals 0. And if that's the case, here we assume that our denominator polynomial is what? It is an nth order polynomial like this. So it is a naught z to the n plus a1 z to the n minus 1 all the way to an. And we assume that the first coefficient, the highest order coefficient a0 is what? Or a naught is positive, okay? So if I'm given this polynomial with assuming that they're not positive, and they say, does this polynomial have any root inside, outside, or on the unit circle? how would you do it without needing to find the roots directly, right? Can you do that with the jury's stability test? Here is the detail for that. And you might say, why do I need to do that? If I have any polynomial, I can just find the roots of that and check whether they are inside, outside, or on the circle. You're right, you can do that. Okay, and MATLAB command roots can actually give you all of the roots, and you can look at their magnitude, see if they're all less than 1 or not. Okay, so you can do that as well. So this jury's stability test, I just explain it just because it can help you later find some ranges for some parameters in the system. Okay, so I'll tell you why it would be useful. Because if the only job of this is to find whether the roots have magnitude less than 1 or not, of course, as I said, you can just find the roots if you know all of those a's, a1, a2, all the way to an, right? So that's not the big deal. The big deal is if there is a parameter, a tunable parameter inside this characteristic polynomial, and you want to know for which range of that parameter this system will be stable, then this table can really help you, because the roots will not necessarily be as easy to find when one parameter is like k and not all of these a's are numbers. If some of them are parameters, then that solution is not going to be as easy. So let me first show you how to form the jury's stability test table and how to check this, and then we're going to look at a couple of examples here. So how do we look at this method? So the way you do it is this. You start from the lowest power, z to the 0, which is 1, and the coefficient of that, which is clearly an, and start going up the power all the way to the zn. So you go a naught, n minus 1, an minus 2, all the way to a naught. That is going to be your first row. Okay, so coefficients from the lowest order to the highest order. In the second row, you just reverse the first row. That's all you do. So if you started with an and a naught at the end, for row 1 here, you do the opposite. You start with a naught, you go a1, and then you end up with an. So row 2 is exactly the flipped version of row 1. What do you do for row 3? Here you fill it with some numbers called b naught all the way to bn minus 1. There will be one less number in it. And again, if you look, row 4 is the flipped version of row 3. You see here, you start with b naught, go to bn minus 1. And the same goes for all other rows. If you look, row 5 and 6, you see that 6 is the flipped version of 5, and row 2n minus 5 is again, and 2n minus 4, again, they are flipped version of each other. And you keep doing it until you end up with only 3 coefficients in that row. If you end up with only 3 coefficients, then that is the end of the table. Okay, so the end of the table is when you're down to 3 coefficients. That row is the last row. You're not going to flip that again, and that is when you can do your calculations now. Now the question is, how do we calculate these b's, c's, and everything? Because the only thing you have in the beginning are just the a's. That's all you have, the a coefficients. So how would you get b's? And this is the formula for it. If you look, it says bk is the determinant 2 by 2 of an minus 1 minus k, and a naught and ak plus 1 as k goes from 0 to n minus 1. Then you do the exact same thing between the b's and you get the c's. Look, so bn minus 1, bn minus 2 minus k, b naught, and bk plus 1. Again, k goes from 0, but this time to n minus 2. As you go, as I said, as you go down each time, you're going to lose 1 coefficient for each 2 rows. So rows 3 and 4 have 1 less than 1, 2. 5 and 6 have less than 3 and 4. Okay, until you get down to the q's, and the q's only have 3 coefficients, as I said, and they are given based on the previous row. If you call them p, right? So qk is p3, p2 minus k, p0, and pk plus 1. Now, let me show you something that might help you remember this formula, because the way it is written, it might not be as clear. So bk, let's go to the table, and I'm gonna show you something that might help you remember the thing. So what is what? What is bk? So let's plug in k of 0. So it's gonna be b naught, huh? So b naught, which is this number, how would you find it? Clearly, it is gonna be a 0, and then what? Because k is 0, it's gonna be, basically this is gonna be a of n minus 1, and this is gonna be a of 1. So what are you doing? N and n minus 1, 0 and 1. Where are they? They are here. Look. Right there. Do you see that? If you find the determinant of an minus 1, 0, and 1, that determinant of this is going to go right there. Now you might say, what about B1? Huh? What about this? If you look at 1, if you plug in 1, let me clean it up and plug in 1, see what you would get. If I plug in 1 for k, what would you get? This becomes a of n minus 2. This guy becomes what? A of 2. But the first column stays the same, a n and a 0. So what would you do for the next one? You pick these two and then these two. And the determinant of these green parts is going to go right there. And so as you move from right to left, what you do is you keep the first column fixed, but for the second column, you move from left to right. Okay, so now B3 is going to be what? It's going to be a n and a 0 in the first column, and then what? A n minus 3 and a 3 in the fourth column, and you keep going. Yes, and the same thing applies for between C and B. So here, if I want C naught, what is it? I need to look at the first column in B and the second column in B, huh? Look at here, you can see that. Because here, if you plug in k of 0, here you're going to get B1, and here you're going to get what? You're going to get B of basically n minus 2, which is exactly there, right? So again, these two will go there. And as you move one to the left, now you keep your first column fixed. Now you move one column to the right for the second column. And you keep doing that, okay? And this way, you calculate all of these coefficients in the table, as I said, until you end up with what? With 3 coefficients. Once you're down to 3 coefficients, you're good to go. Now you can do your calculation. So what are the conditions for stability? The first condition is the magnitude of the last an, which is that constant, should be less than a0, and a0 is positive. Remember that a0 is supposed to be positive here. Good? So that's the first thing. An should be less than what? A0, magnitude of an. Then what? Then you need to what? You need to look at the, evaluate this polynomial p of z. You need to evaluate this p of z, which is this polynomial, at z equal 1, which is basically a point on the what? On the unit circle. The value of this pz should be positive. At z of negative 1, which is another point on the unit circle, if n, which is the highest order of this polynomial, if n is an even number, p at negative 1 should be positive. If it's an odd number, it should be what? Negative. And then the same thing that you applied, rule 1, that the biggest n index is bigger than the lowest n index, the same thing should apply for all the other columns. So the biggest b index, which is this one, in magnitude should be what? It should be bigger than the lowest b index, which is b naught. The biggest c index, which is cn minus 2, should be also what? Bigger than the lowest c index, which is c naught. And finally what? q2 also should be in magnitude bigger than what? q0 or q naught. And if that is the case, guess what? then you are good to go. You can basically do that. Now, the first one is different. Look, the first one, an is less than a naught. For these other ones, the highest index is bigger than the lowest index. So they are basically the opposite inequality. So pay attention to that. So if all of these conditions are satisfied, then guess what? Your system is stable. All the roots are inside the unit circle. But if one of these conditions is not satisfied, then you will not be stable. At best, you will be what? Marginally stable. You're not going to be fully stable. Okay? So let me show you an example here. So first example is this. Here, your polynomial of the transfer function in the z domain is this fourth order polynomial. Now, of course, you can use MATLAB roots command and find that, hey, look, all the roots of the system are less than 1 in magnitude, so the system is stable, end of the story. Yes? But can I form that table and see if with that table I can get the same thing? Yes. So here we need to write down the A's clearly. A0 is what? A0 is your basically coefficient of the highest order, so it's going to be 1, and you see it's positive, of course, based on the condition we have. If it's not, you can divide both sides. Then what? Then a1 is 1.2, and then you keep going, negative 1.2, 0.07, 0.3, and negative 0.08. So you get all of this, and clearly n is what? N is 4 here, okay? So this is what? This is your n. N is 4. So when you look at the third condition, p of z at negative 1, that should be also positive. Okay, I'm talking about right here. You should basically go with that one. So first thing is, before I even look at the other things and form a table, is magnitude of an less than a naught? Well, an is negative 0.08. Magnitude of that is clearly what? 0.08. And magnitude of a naught is what? Is clearly 1. So this is valid. So condition 1 is good. So now I can look at what? Look at the second and third conditions. And then for B's and C's and Q's, I form the table. So what about P at 1? If I plug in a 1 in this polynomial, clearly you see the value is going to be 0.09. Which is what? Bigger than 0. So condition 2 is also what? Satisfied. Then I plug in P of negative 1 at Z of negative 1. If you calculate it, that is going to be 1.89. Again, is positive. And since n is 4, is an even number, that condition is also what? Satisfied. So far, the first 3 conditions are good. Now it is time to what? To form the tables. Okay, so let's go ahead and form the tables here together, form this table, and see what we are going to get. Okay, so here is the table, and I started from, as you can see, A4 all the way to A naught, and in the second row, I go from A naught all the way to what? To A4. Now, if you remember, the B row has what? Has one element less. So for B row, you start one column to the left of the A on the right side. You see here, this last column is empty, and you start here. And the first number you do is B naught, correct? And if you remember, going back to the discussion we had, B naught was what? B naught was an a0 and then a1 and a basically n minus 1. So it was this part. Okay, so let's go back and do it right here for this example. So here the numbers I need to pick are clearly these guys and these ones. We need to find the determinant of that, and that is going to be my B naught, which is going to be sitting right on the fourth column. And so if you find the determinant of B naught, which is negative 0.08 times negative 1.2 minus 1 times negative positive zero point 0.3, your first number that you need here is going to be 0.204. And you know what? Let me get rid of these. Here we go. That's this one. And then you can calculate the other numbers one by one as well. So you go all the way to here where B number 3, so that's B0. B number 3 is going to be negative 0.994. So let me avoid the 0 for here and just write it like that. If you want B2, it's going to be 1.176. And B1 is going to be negative 0, 0, and then 7, and then 5, 6, like that. Okay, so these are your B's. Now in the next row, you have to invert it, so you can go like 0.204. And then this is going to be that negative 0.756, and then it's going to be 1.176, and here is going to be negative 994, like that. So B rows are found and they are displaced. Now we can go to what? To the C's. Now for C's, we do the same thing. So the first C is basically going to be the first two columns in B, right? So you're going to get these four numbers. And from there, determinant of that is going to give you C0, which if you calculate C0 is going to be 0.315, like that. And then C1 is going to be negative 1.184. And C2 is going to be 0.946. And look, you're down to three numbers. When you're down to three numbers, you don't need to continue. Here, that's it. That's the end of the table. And if that's the end of the table, now we go back and look at those conditions that we have. What were the rest of the conditions? The conditions were that the highest coefficient or highest subscript, B's, C's, Q's are bigger than their lowest ones, okay? So if we go back here and look, clearly the A column was okay, but here we need to look at the B and the C column, and you see that this is your B number 3, this is your B number 0, and clearly the magnitude of your B3 is absolutely what? Bigger than B0. So this column is good. And then if you look at the C column also, you can see that the magnitude of C2 again is bigger than the magnitude of what? C not in here. And so we can say that this condition is also what? Satisfied, where you can see both of them here. If that's the case, since all five conditions are satisfied, the system is stable and it has what? It has basically all roots inside the unit circle. And clearly, if you ever ran the command roots on this, you can see that, of course, they are. They're all within the unit circle. So now, as I said, you would ask me, hey, all these calculations, all these A's, B's, C's table, all these five conditions just to check whether these roots are inside the unit circle or not. Guess what? We just use MATLAB and it gave us all the roots and it's over. We should not use all these calculations. And you're right, absolutely. But the thing is, MATLAB can find all of those roots and find them numerically for you. if all of the coefficients of this polynomial pz, they are all numbers. If one of them is a parameter that is under your control and you want to find for which range of that parameter the system is stable, you cannot really necessarily find the roots all, okay? So that's where this method shows the beauty of it. So here, the system I have is a system with unity feedback, where the G is the feed-forward transfer function is this, and it has a gain K that is under your control. The closed loop transfer function C over R is going to be G over 1 plus G in this case, and there is no H feedback. So it is going to be this transfer function. And clearly you see that the denominator, which is the characteristic root, is a second order polynomial. Now, when it's a second order polynomial, here you have three coefficients, right? And what are these coefficients? Clearly a0, which is the highest order, that's 1. And a2, which is the last one, is this guy. And this one here, this one is a1. Okay, if you ever need it. So do I need to form a table here? No. Why? Because I'm already at three coefficients. When you are already at three coefficients, no table is needed. All you need to check are the first three conditions. That magnitude of an is less than magnitude, that a0, p1 is bigger than 0, and p negative 1 is positive, or p1 is bigger than 0, I'm sorry, and p of negative 1 is also bigger than 0 for even numbers of n, and it's less than 0 for odd numbers of n. So in this case, since the system is already order 2, you don't even need a table. Magnitude of a2, magnitude of this one, should be less than a0, which is 1. So this is your first condition. And clearly, if you solve this, you know how to do it, right? That means this inside term, it should be between negative 1 and positive 1. And so one time you solve it for negative 1, one time you solve it for positive 1. If you do so, it gives you a range of k between negative 5.1 and 2.39. So as long as k is in that range, your first condition is satisfied. Then you go to the second condition. P at 1 should be positive. So you plug in 1 there, and it is going to be this number. If this is positive, means k has to be positive. So this is your second condition. And finally, the third condition is p at negative 1 should also be positive, because n is 2 in this case. You plug in negative 1, you get this guy. That should be positive, which means k should be less than 26. And now if you basically put the intersection of these three conditions, this one, and this one, right? You have three conditions for stability. The intersection of these three ranges is between 0 and what? 2.39. So as long as your k is between those two numbers, your system is going to be what? Stable. This kind of analysis is not something you can do easily with MATLAB numerical solver roots command or something. So that's where this jury's stability test is really what is really useful to you. And you might say, well, do you have any example of any system for which it tests like in stable, huh? Could you show me an example of a characteristic polynomial that when you do this jury test, it goes on a stable or critically stable or something? Yes, let me show you that. Okay, so for that, here, example 3, we're going to look at a system that is critically stable. How do we know that? So here we have a system of order 3. Okay, so n is 3 here is odd. And a0 is again 1 positive, and a1, 1 negative 1.1, a2 negative 0.1, and a3 is 0.2. The first thing is a3 in magnitude should be less than a0, and it is. 0.2 is less than 1, so first condition is satisfied. P of 1 should be positive. Well, if you plug in 1, clearly you get what here? You're going to get 0. This is the tip-off. So if this condition is absolutely positive, that is one more toward the stability. But if this condition is not satisfied, but at the boundary, at the border, so it's not bigger than 0, it's equal to 0, that could be a sign that your system is critically stable if the other test won't fail. Okay, so if P of 1 is bigger than or equal 0, in this case equal 0, that might be a critically stable system. So we need to look at the other conditions, see if they are valid. So P of negative 1, if we calculate it, you see it is negative, and that is less than 0, and it should be because n is an odd number, so that's good. And here, if you go and calculate the table, right here, you have 4 numbers. So remember, like last time you had what? You had, let's see if I can move this. Last time you have 5 numbers, so you went for uh, 3 sets, right? So 1, 2, 3, 4, and 5. This time you only have 4 coefficients. So all you need is to just calculate the B row, okay? The B naught, B1, and what? And basically B2. And so here, all you need is to go from, on the first row, if you remember, you start from the last A and go to the first A. So if you want to form that table, here the first number that you have is 0.2, right? And then negative 0.1 and negative 1.1 and 1. The next row you reverse it, so you make it like this. And now your first B here is going to be what? Your first B is going to be the determinant of this portion. It's 0.2 times negative 1.1 plus 1 times negative plus 1 times 0.1. If you calculate it, you end up with basically what? With negative 0.12, which is that number right down there. So here, this number is going to be negative 0.12, and then you can move on and so on. The last number that you need to compare to this first one, that is going to be the first column and the last column, which is clearly 0.04 minus 1, and that is negative 0.96. That is this one. And B1 here doesn't matter, but if you want it, it's that 0.2 and 1 and negative 1.1 and negative 0.1. So that's like negative 0.2 and negative positive 1.1. So you're going to get 1.08. Which doesn't matter. What you need is to compare the magnitude of this one, and the magnitude of this B2 has to be less than what? Bigger than the magnitude of B0, which is this one, and it is, as you can see. So you see that all conditions are satisfied except for one of them, which is only marginally at the margin. It's not satisfied, but it's not also less than 0. It's equal to 0. That is an indication that your system is what? Critically stable. And if you look at this system, of course, it has a... And why is it that it's critically stable? Because when P of 1 is 0, what does it mean? It means 1, Z of 1 is one of your roots, and Z of 1 is on the unit circle. And remember, on the unit circle means what? It means it's critically stable. So if you decompose this, it is going to be Z minus 1 times what? What are the other roots? So here I decompose the polynomial. One of the roots is 1. The other quadratic part is this. And clearly, if you see here, it's b plus minus b squared minus 4 times AC divided by 2. So this is like 0.9. And of course, so one of the roots is going to be like 1 over 2. So one of them is like 0.5. And the other one, which is with negative 0.8, so it's going to be negative 0.4. So you see that one of the roots is on the circle, the 2 other roots are inside the circle, and clearly the system is what? It is critically stable. Okay, so you learned when you can look for critically stable, and for unstable, Here we're going to look at this last example. This is your polynomial this time, and these are the a's. Clearly a1 a naught is positive, and magnitude of a naught is bigger than a3, so the first condition is satisfied, which is this, less than, sorry, less than a naught. This condition is satisfied. So now you go for p of 1, plug in 1 in this, and you get negative. Negative means 1 is not a root, and it is going to have a root outside the unit circle. And as soon as you get that, you're going to stop right there. That means the system is what? Unstable. Done. Okay, you do not even look at any other condition, because typically what we care about is if the system is stable, then we move forward. If it's not, then we have to do something about it. So here we learn that the system is unstable, and that's all we care about. Okay, so this is the jury's stability method and the overall analysis for stability for transfer function of a digital system or discrete time system. Hopefully you enjoyed this lecture, and I'll see you in my next video. Thank you.